Okay, yeah. Welcome everyone that made it here this early. Just some opening words before we go to the first talk. Yeah, this is the workshop, it's the demos. Deep look at the role of demonstration quality in imitation-based robot manipulation for the RSS conference. So yeah, here the overview of the organizers. We're a different bunch from industry, academia, and all over, mostly Europe and Australia, so that counts. The world, some familiar faces, some of us are here, some are online, and yeah, we hope to interact and give you a good workshop. So why we thought of this workshop is that now that we can do better manipulation that I have ever seen since I started in robotics some years back. However, the imitation learning is not new, but the quality, the performance we get with new methods is new, and the quality really is emerging for a bottleneck of how the imitation learning performs in the task success. And there are no shared metrics, vocabulary, or best practices. Everyone has a bit of a gut feeling what works, what doesn't. At least that's our impression, and we hope to gather these learnings and share between each others. And yeah, that's why practical lessons and failure modes, you'll rarely see them in the papers. Hopefully we can share some here. And we have 4 invited talks, and we had 8 accepted works. 4 of them will be spotlight talks, and every accepted work is a poster. We're still going to figure out how we put the posters up, but we still have time for that. So we will see how that works. And then we have one at the end, Mentimeter group session, where we also aggregate some of the learnings, as well as decide about the most useful practical information award that we are sponsoring from Inca Robotics. Basically, the idea here is to facilitate sharing information. So everyone that has a poster is eligible for this award. And everyone that is attending votes who gets the award, except for the organizers, to avoid any corruption. So the idea is really what, when you go out and talk to the posters and to each other, who gives you the most practical information that is useful for you, and then when the voting comes up, you vote for that guy or for that poster. So that we hope to facilitate that we share as much as possible about what works and what doesn't work. And the price is this MetaQuest 3 here, as well as our Learning Stack license, which we have a very quick pitch video here, and then we stop with the sponsorship until it's time to vote. So the idea is that at Inca Robotics, we built this stack that helps with robotics learning, which is platform agnostic, and you can basically deploy it on any platform and with any hardware. Some asterisks apply, of course. There are always some limitations to this stuff. However, we did put it on some, as you can see here. You can also have hand tracking and hand control. You can map the controllers to the mobile base, and you're then also able to easily load and deploy different policies, which is also great to compare different methods. So this is more the plumbing than a specific method. So you can load vision model diffusion, you can load GROOT, you can kind of load different methods and then compare everything based on imitation learning. You can basically deploy and extend, and this also allows you, like we used it, for example, in the case where one policy fails, and then you just swap it in the GUI and the other policy succeeded. Here in this case, we swap between the basketball and the wiping policy. But enough about that. A quick overview how we're gonna start today. We're gonna start with the talk after I'm finished talking from Nadia. Then we're gonna have 2 spotlight talks, and then another invited talk. And then we're gonna have the coffee break where we're gonna see the 8 posters, or however many manage to show up on time. And then we're going to have another invited talk at 10:30. That's the end of the break. Second spotlight session. the final invited talk, and then we have the, we call it structured group discussion presentation, but it's basically a Mentimeter session where we aggregate the findings of the day. So we have it on one fancy word cloud, as well as the award and the voting for who gets it. Let me introduce you. So our first speaker is Nadia Figueroa. She's an assistant professor in mechanical engineering and applied mechanics in the University of Pennsylvania, where she's also a faculty member of the GRASP laboratory. And before joining Penn, she was a postdoctoral researcher at MIT with Professor Julie Shaw and completed a PhD at EPFL under Aude Billard. Her doctoral thesis on robotic learning and complex tasks was finalist for the 2020 George Gray Girard PhD Award, and her work has received several distinctions, including the Best Student Paper Award at the RSS. So she's very familiar with this conference. And yeah, please join me in welcoming Nadia.
All right. Can you hear me? Can you hear me well?
Yes.
All right. Okay. Well, thank you so much, Michael, for that introduction and for inviting me to give a talk in this workshop, which I like the topic very much. So the title of my talk is The Less Your Imitation Learner Knows, the More High Quality Demos it needs. So today I will, based on this title, I will present kind of like my views on the need for such vast amounts of high quality demos in the current imitation learning algorithms. And in particular, I will argue that the required quality, coverage, and quantity of demonstrations is actually determined by what the imitation learning algorithm already knows, or in a more kind of like provocative reframing, is a function of the physical naivety of the imitation learning algorithm. And I will not just make these claims. I will actually corroborate this through a couple of lines of work that we have developed in my group in recent years. So what do I mean by what the learning algorithm knows? By this, I mean I refer to constraints and such as stability and safety, and physical structure such as geometry and physics that are encoded, that can be encoded in any imitation or any other type of learning algorithm. So let's consider the data trade-off for let's say a single short to mid horizon task. So I created this graph, which I mean, I don't have any, it's not published anywhere, or like I just kind of like, this is from my experience of what I've seen over the years. So the x-axis that you can see here, this is what I call the constraint awareness, right? So the more constraint aware your learning algorithm is, the less data, the less high quality data. You always need some good quality, or maybe like it could even be suboptimal. I saw some papers there that are learning from suboptimal demos. But in general, the more constraint aware your learning algorithm is, the lower the high quality demos are needed. And as we go along the x-axis, so basically the more unconstrained your learning algorithm is, the more high quality demos that you're actually going to need. Right, and this is I created this graph based on some of the very popular and highly performant imitation learning algorithms that have been released in the last couple of years. Most of them actually at RSS. Right, so we all know the diffusion policy, which is essentially the visual motor policy, where the input is RGB images, pass them through some encoder. That latent representation is then passed through some MLP head that gives you some actions, right? And so this was a very popular and a method that showed very interesting generalization, but at the cost of the number of data that you need, right? So for example, in one paper where we try to understand the generalization of this method, we simply to do a pick and place task from, for example, grab the mustard bottle and put it on the plate. Simply to have it working in this green region, we needed 115 demos, right? So here the camera is somewhere here. And essentially what it's learning is learning this kind of like end-to-end vision motor policy from RGB to action or to action chunks. And what's interesting is that if we only train it with on the red hand side of the workspace that I show, on the green hand side of the workspace that I showed, if we test it now on this side, we all know, like those of us that have tried out to work with diffusion policies or any of this kind of like what I call physically naive imitation learning algorithms, it's not going to work, right? Like it's not going to generalize unless you actually given more data on this side, and this is more kind of like on the spatial generalization. And so I placed the diffusion policy somewhere here at the top. Right, so like a very unconstrained in the sense that we don't need to introduce any knowledge about what the robot needs to do or about constraints, nothing. But we need a lot of data in order to get it to work, right? In order to even do very simple short to mid horizon tasks with some spatial generalization. And for those of you that are interested on this experiment, this is actually an experiment that's where we try to understand this problem, this spatial generalization problem, and we developed a method to kind of like recover from these out of distribution scenarios. I'm not going to go deep into this, but just if any of you are interested, essentially we modeled the probability distribution of the data as a Gaussian mixture model, and then use a gradient of the likelihood to bring the robot back, and that's our recovery policy. And then we can even do continual learning on this. So if you're interested in this work, we have this paper here. And one thing that we can see is that this, of course, there's low spatial generalization. Like if you want really high spatial generalization, in the sense that the object can be anywhere on the table and the goal can be also anywhere on the table, then we actually need kind of like thousands of demos in order to get this, what I call the high spatial generalization. And this was the next year at RSS 2024. These researchers et al. Introduced a 3D vision motor policy, right? So the 3D diffusion policy, which now takes into consideration now the 3D point cloud, right? Like a 3D point cloud as the inputs, pass it through some 3D encoder. And now they achieved the same level of generalization as the diffusion policy with the RGB image inputs, but with much less amount of data. With the caveat that it still kind of like suffers from this low spatial generalization. So this was demonstrated in the subsequent paper from RSS 2025, which I like very much, Demo Gen. Yeah, I think this is not the correct authors, but here they actually tested the 3D vision motor policy, and they showed that in order to get kind of like high spatial generalization, even just within the table, like with doing pick and place tasks with different goals, you needed kind of like hundreds of demos in order for a 3D diffusion policy to perform correctly. And one of the figures that I liked a lot from this paper was this figure 3, where they actually show and test they show this quantitative benchmark. So full means like they fully randomize the object locations and the goals and all over the table. Only half of the table is randomized in the location, and fixed is only kind of like in fixed locations. So you can see here that obviously the more information you add, or like the 3D diffusion policy, I put it somewhere here. Right, it's like a little bit towards the left of the unconstrained, because it's already taken into consideration that okay, 3D geometry is interesting, right? 3D geometry actually helps, and so you can see there, like you require much order of scale, less number of demos, but it's still in the hundreds. So what about the methods that are here, right? So like for me, one of what I'm super interested in general is to come up with methods that require the least amount of data, right? Like with one demonstration, it should be sufficient for the imitation learner to be able to learn the interesting properties of the task, of the demonstrated task, and be able to generalize. And this is what we did. So we have one of our latest motion policies. It's called the elastic motion policy. And we presented this one at RSS, at IROS 2025. And this one in particular, that's where we leverage constraints in the imitation learning algorithm. In particular, we enforce stability and convergence guarantees in the motion policy. And we also use some geometric trajectory warping in order to make it adaptive, in order for it to adapt to changes in the workspace to be able to achieve this spatial generalization. So now I'm going to talk about this imitation learning approach. So this really comes from this notion that I started working on during my PhD with my PhD advisor, Aude Villard, of using dynamical systems as action representations. So this idea or this paradigm simply states that we assume that the demonstrated trajectories and the motion that the robot should perform can be driven by a virtual autonomous dynamical system of this form. Very simple, first order differential equation. X can be the states of the end effector. It can be the SE3 space. It can be joint space. At this point, it can be like any kind of like parametric space that has a proper metric. But in the simplest form, essentially, we can say X is position, X dot is velocity, and f of X is this function that can generate or can be represented by this vector field that shows that from anywhere in the state space, the robot can converge to a target and be shaped based on a trajectory that is provided by enforcing this constraint. So this is kind of like the asymptotic stability or convergence constraint, where we would want the robot to converge from anywhere in the state space to the target X star. And what's cool is that we can introduce these constraints, these stability constraints, using Lyapunov theory or even contraction theory, like for more interesting tasks that are not just goal-oriented. We can also enforce safety via boundary-based invariance and viability theory. And this type of motion representation has a very natural and beautiful connection to energy shaping and compliant control. So essentially what we're doing here with these dynamical systems is that we're framing the imitation learning problem as a system identification, because what we're saying is that these trajectories represent some virtual autonomous dynamical system. So then we can use tools from system identification, which are essentially convex or optimization or constraint optimization formulations to train or to learn these vector fields with these global asymptotic guarantees. So the whole idea is we gather some data, and the cool thing about this is that we don't need that much data. We can do it with like 3 demos. We can do it. We have methods that with only 1 demo, it's enough to be able to learn a vector field that is globally converging from anywhere in the state space. So we have works that I've developed works that can model these complex nonlinear trajectories in the Euclidean space. We can also shape them such that they become a little bit more stiff around certain regions of the trajectory. We can also encode limit cycles. We have these methods working also in the SO3 space basically on the tangent space of the quaternion attractor. So now combining these two, we have SE3. So we have SE3 dynamical system motion policies. We can even learn them in joint space and even in some latent space. So really like this representations is quite scalable in terms of the dimensionality or the state space that we want to control our robots. So we have multiple formulations. One formulation that I'm going to present today, which is the basis of the 2 works that I'm going to talk about in a bit, is this mixture of linear systems. So essentially, for a nonlinear to represent this nonlinear trajectory, we're assuming it converges to a single goal. As a dynamical system, we can represent it as a mixture of linear systems, where each of these linear systems each of these ellipsoids that you can see here are essentially defining like the activation or like which linear system to activate when you're really close to this region, and then as you come further away, then it essentially acts as a mixing function. So here, these are some constraints that we derived in order to ensure that the mixing results in a globally asymptotically stable system. We use here Gaussian mixture models to represent these little linear clusters in a nonlinear trajectory. And we have recently, we have methods actually to using parallel sampling, essentially Markov chain Monte Carlo methods that can automatically estimate the number of Gaussians that you need to represent these nonlinear trajectories, and also place them such that each of these Gaussians represents linear flows in your data. And then, so this is kind of like a two-stage learning. Once we train that, and one thing that will become interesting later is that this algorithm, the DAM, which is called a directionality aware mixture model, it runs quite fast. So it runs in less than a second, depending on the number of data that you have in your trajectory. So once you fit these Gaussians, the Gaussian mixture model on your trajectory data, then we solve for these parameters, for the A's and the B's of these linear time invariant systems, using convex semi-definite programming. That's the tool that we kind of like borrow from system identification, using the typical objective of reconstruction accuracy that we use for imitation learning. But now these parameters are subject to these constraints, right? So like this constraint enforces the energy dissipation, essentially that for your dynamical system, you have a Lyapunov function that enforces this energy dissipation, and we enforce that all of these systems converge to the targets. And once we mix all of these parameters, then we get these really beautiful vector fields. So one of the cool things about this approach is that we have a couple of data with a couple of demos. We train these vector fields, and then we have this stable, safe, and compliant motion. So the robot can react to external perturbations. It can even react or figure out how to change its motion based on like small changes in the attractor. But the caveat in this method, and a lot of like these primitive-based, like dynamic primitive type of methods, is that they really fail at spatial generalization. For example, here, this is the extension of this algorithm that I talked about in the last couple of slides, but now to SE3 space. So now also defining a dynamical system in the tangent space of the quaternion attractor. So here with a single demonstration, full SE3 space, the robot can very easily reproduce it, which is great. But if we change, as you can see here, if we change the location and the orientation of the attractor, then this vector field is really not going to morph or generalize without us really like imposing those constraints into the learning algorithm. So it kind of like fails with these intra-task spatial changes. So that's what we solved in the elastic motion policy. So here, the whole idea is that now we actually use a UMI gripper, which is, so there's also a beauty of this dynamical system framework that it doesn't really matter. You can gather data from kinesthetic teaching, from teleoperation, or even from this UMI gripper style demos. And essentially what's going to happen is that the vector field or this motion is kind of like going to smooth out your trajectories, which results in a very nice and smooth motion. In this elastic motion policy and this new work, what we did was we use a UMI gripper, and we leverage some of these novel methods, for example, grounded SAM, to figure out which is the object of interest. That's where that we need to track or as our attractor in this SE3 space. We use foundation pose to actually track it. And we define this key pose, which is kind of like the location of the position and orientation of the object that represents the attractor. So this is what we do during data collection. And then essentially when we run this policy, so after data collection, we train it once. We train once to fit the GMMs, then fit the linear system matrices. And during execution, we're tracking in real time the SE3 pose of the object. So essentially, we're tracking in real time the attractor of the dynamical system. And if there is a change in the with respect to the demos, then we update the parameters in almost real time. Essentially, like here, this update can take up to like 50, can be as fast as 50 hertz, but right now we set it to 30 hertz because that's as fast as we can get the perception going. And just to give you a little glimpse of how this works, essentially we have the original policy. Now we introduce constraints based on the objects of interest. So and we represent those objects of interest as SE3 frames. Here, the bottom can be a via point. At the top can be like an initial and a final object location. And if any of those frames change, then what we do is we essentially manipulate the Gaussian mixture model, which is the one that defines the shape of the vector field. And then this manipulation is solved through a very simple convex optimization problem that is essentially using a very interesting method from graphics, which is called Laplacian surface editing. So essentially, what we're doing is we're parameterizing the Gaussian mixture model as a kinematic chain. And then we're modifying locally those parameters. We can shrink or expand the Gaussians and even rotate them based on the change in these geometric constraints. So what's cool about this method is that from a so we did this. We applied this to we also applied to the orientation space. This initial warping idea, we published that at Coral 2023. And the elastic motion policy essentially extends it to the orientation space as well, as you can see there in these animations. And then we also reformulate one of the optimizations that we need, which is this kind of like convex optimization to learn the P matrix for our constraints. And yeah, so here I can show you some cool video. So here you can see from a single offsite demonstration. The robot on the video on the top right, this is a completely uncut, not cherry-picked video where we're just running the policy and the policy is adapting in real time, right? So you can see there with a single demo, the policy learns the parameters and figures out what is the object of interest, and if that object of interest is changing, then the adaptation is happening of the parameters is happening in real time. And here you can see also like this is actual real time adaptation. So here you can see a pouring task, single demo, pouring some fake liquid into the pot. And here you can see the video. This video is also not this is not even X2. This is a real-time video. So you can see the real-time adaptation. In this particular case, we're tracking the pot with foundation posts. So the adaptation is as fast as our perception system. And what's one cool thing is that, okay, so we can, in this particular case, we can also learn multi-step tasks simply by being able to segment these tasks into goal, to segment a long horizon multi-step task into these kind of like into goal-oriented tasks. And here in these videos, you can see that with a single long horizon, in this case, kind of like three-step goal-oriented tasks. The robot learns kind of like each of the skills and is capable of reacting in real time with changes in the locations without us having to provide any new data. Just with a single demonstration, the robot can adapt spatially to any changes in the object that you would need to transfer from point A to point B. So this is very cool, right? So this is where we get the EMP, this elastic motion policy. Of course, this execution that I showed The high level kind of like learning is simply just like mimicking exactly the sequence of goal-oriented tasks that were segmented from the data. There's not much intelligence there. So the common critique that we get for people, for us, I mean, people that use that like structured imitation learning algorithms or kind of like primitive-based approaches, is that these approaches do not really scale to longer horizon, kind of like more complex tasks. Right. And then that's here. I want to explain this a little bit further. Right. So like if we now expand this 2D graph that I created on the data and let's say structure or constraint trade-off across now task complexity, we can see here that the more complex the tasks and the longer the horizons, then essentially for the unconstrained methods, they actually work if you give them more data, right? So like that's the premise of all of these startups that we've seen, or in all of these startups that are also just focusing on data collection. So like the more data you have, the more complex tasks that you can perform. But here you're putting a lot of effort on the data collection side, right? So I'm just going to mention this work quickly because I think it's kind of like a counter to this critique. So we showed in very recent work that we published at ICRA in a couple of months ago, SimSkill, which won ICRA Best Conference Paper Award and Best Paper on Planning and Control. We actually showed that we can automatically learn kind of like a symbolic plan from symbolic predicates, operators, and these stable SE3DS motion policies, which is kind of like the underlying policy for the elastic motion policy, simply from 5 minutes of unlabeled play demos. Then we can kind of like plan symbolically to compose these skills, and we can even recover from failures in real time and on very long horizon type of tasks. So I'm just going to show you so that I don't go over my time. So here you can see, for example, we can from 5 minutes of play data, the whole idea is that the demonstrations are valid actions, right? So like the video that I showed at the beginning, the demonstrator is showing valid pick and place actions of objects going from one point to the other, and the premise that we have in terms of the segmentation or being able to extract like a structure for planning, for long horizon planning, is that the objects that are that stay close to each other after motion, so basically when their velocity goes to zero, are somehow connected, right? So they are like preconditions and effects of the other. So here we can see how I'm going to show you two videos now. So we can learn that this SimSkill algorithm, what it does, it essentially learns the preconditions and the effects for different goal-oriented tasks in just play data, where we're assuming that we have kind of like a valid execution of skills. And then we can zero shot any long horizon trajectory. So here we tell the algorithm move banana to plate, and then essentially it figures out how to do it. So here the underlying policy is an SE3 LPVDS. As you can see here, the planning is also reactive, not just the motion, and not just at the motion level. We can also enforce a collision avoidance by reshaping the vector fields very nicely. And the learned actions are actually then once you give it a goal, we create a graph from all the demos, and we use very simple A-star search to algorithm to deploy it. So here I'm going to show this last video of like telling the robot now to the goal is the lid closed and then move all food to the pan. It essentially runs through, it creates a graph of all of the different skills that it learned, all of these different primitive skills that I learned that are parameterized as SE3 LPVDS, and simply goes through this long horizon plan length of 10 demos. So if you're interested in this this work, this is essentially a combination of compositional. It's compositional like task and motion planning. It's reactive like VLAs, and it's certified in both the planning and the skill levels, and it's quite data efficient. So from 5 minutes of data, we could learn a number of skills, and then chain them to create long horizon tasks that the demonstrations actually never demonstrated before. And here we can also kind of like this just another interesting video showing the same algorithm where all we here the skill is just to open the door, but it can recover basically. So it has this also this recovery property. So I'm gonna end here. I hope I convinced you that structure is interesting, and it's not, and this statements that hyperscalers typically say that yeah, you can't scale like structured algorithms is actually a fallacy. One can do very cool things with structured algorithms. It all depends on where you introduce the structure. And I just want to acknowledge my funding sources and my wonderful students who make all of this come true. Thank you so much.
Thank you so much. Any questions? Probably best to come to the microphone and to this camera.
Hi. It was a great talk. I feel like I learned a lot within a very short time. Thank you.
Thank you.
But I have two questions, basically interconnected questions. First one is, how do you establish a lower bound on the quality and quantity of data needed for learning? Because it's very task specific and it's very algorithm specific. So how do we even like begin to establish that? Second is, if you say you provide X number of demos and it doesn't work, how do you debug why it's not working? Is it the quality or quantity, or if algorithm is not performing well enough? Where do you stand on that?
So for the lower bound, I'm assuming that you mean that kind of like that this graph that this picture that I created. Yeah, I mean that's it. I would love to actually do this exhaustively and kind of like, you know, from all of the algorithms that exist, figure out what are the lower bounds for a particular type of task. That's why the very first 2D graph, I specifically defined it as kind of like very simple, short to mid horizon tasks, typically kind of like just pick and place. And then the 3D graph starts kind of like creating, like going into more complex, you know, kind of like longer horizon, even contact rich tasks that I didn't talk about, but we can also do that. So that is definitely I don't really have like a satisfying answer, I think, for you on that. Like the only thing that I could say is that with these algorithms, you kind of like already know like the assumptions that you're making on the demonstrations, right? So for example, for these dynamical systems that are goal-oriented tasks, we're assuming that all the demos are going to end up with the same goal. All the demos are going to end up with like a 0 velocity at the last point, or you massage them to actually make them like that. For some of the algorithms, self-intersections are not possible because it's kind of like a very simple first order differential equation, so it can't disambiguate between like multiple velocities at that same point. So then for that you can, I mean, there's methods to deal with that. But the assumptions of the data are very clear from from the constraints that you're imposing on the imitation learning algorithm. So indeed, it does have like they're not as general, right? There's not as general as kind of like a non-constraint. So there's only like a class. For each different method, there's kind of like a class of motions that it can actually perform. So from there, like you already know, like, okay, so if it's not, if it didn't convert, if it's not working well, it could be that that there's a problem with as you said, maybe like you need a little bit more points on your trajectory. If you're just using one trajectory, if you have very sparse data, just like maybe 10 or 20 points, like you will see in the Gaussians, in the probability distribution, you actually see that there, there's like a mass kind of like lacking in that in your trajectories, and that's why your vector fields are just really not fitting very well. So for my methods, for these dynamical system methods, like we know when they will work and when they don't. But the problem is in the other kind of like on the other extreme, like these unconstrained methods. I think the only I really like that paper that I talk about, that it's not even my paper, the Demogen, that's they do a very nice study of like the spatial generalization and how much data do you actually need, or at least like how diverse that's actually what is exploring. I hope I answered the question.
Do you have a way to like rank trajectories basically, like, because the quality is what we're focusing on in this workshop, right? Like, do you have any way to like establish what is good quality and bad quality in demonstrations?
So yeah, I mean, one way of ranking the demos is essentially, since these the way that we learn these motion policies is with convex optimization of the parameters, so it's very quick. So what we can do is essentially use even the metric, like the objective function of like how much the velocities are deviating from the actual from the actual demos. And the whole idea from this representation is that the velocities of the trajectories should essentially follow kind of like a continuous flow. So if the velocities are going all over the place like this, then you already know like there's so much variance, right, in the motions that's not going to work for this algorithm. So you can actually use that, like the variation in the velocities on each of the trajectory points, that essentially will represent it as like, it's kind of like discrete motion. So like this data is not really going to work well for our algorithms. All right.
Thank you. You have one more short question? There's one more short question there, and then we will move on. So take it.
Very nice talk, Jeff Bingham. Actually, kind of following on what you already answered, it seemed that your technique has an advantage in that you could actually analyze sort of the sensitivity of the data that you collected to the actual quality of the behavior you get out. Have you done anything like that so far?
We have not, but that's a pretty good idea. Yeah, for sure.
Hi guys, my name is Leo, first year PhD at the University of Maryland. I'm gonna present my work, Human Ego, zero-shot robot learning from millions of human egocentric videos. The objectives of this paper is straightforward. If we only have 30 minutes of human egocentric data to train robot policy, what representation and architecture should we use will maximize learning efficiency? Human Ego is designed to answer this question. Okay, let's get started. For human to robot transfer, all you need is someone wearing meta-red glasses, collecting minutes of data with their own hands. During pre-processing, first we use area slam to transform everything into a steady word frame. Second, we do hand-to-gripper mapping to translate human hand motion into gripper actions. For visual part, we do arm impinting to remove the arm, then reading the hand and object back as colored key points. It all runs on off-the-shelf foundation models, give us an embodiment agnostic observation. Furthermore, here's a fun little experiment. In this task, I only glance at the scene once and then look away and finish the whole thing with no vision at all, which tells us vision isn't that necessary. What really needs is spatial observation. So based on that, we introduce interaction-centric tokens, or ICT. We treat every hand and object as an entity, and each token encodes its type, its pose, each hand's pose relative to it, which captures the manipulation state. This turns the problem from inferring 3D dynamics from pixels into learning actions from explicit spatial relationship. is unified, self-sufficient, variable length, and embodiment environment representation. For architecture, we use flow matching, and we also add 3 auxiliary objectives sharing the same encoder: object motion, 2D twist, and latent consistency, trying to squeeze more signals from the same demonstration and force the encoder to learn the causal structure of the manipulation. So this is the final architecture. So now let's take a comprehensive evaluation of our method. We evaluate on 4 real-world tasks against 6 baselines, all trained on 30 minutes of data per task. Here is the result. Human ego achieved 92.5 success rates, the highest on every single task. And even with just 15 minutes of data, it still hits 75, outperforming any methods, including ACT trained on RoboType data. Here are some real-world video clips. We also ran a zero-shot generalization study, like cross-embodiment, environment, and cross-setup. In every case, human ego generalized zero-shot with almost no drop, staying above 85%. Here are some examples of robustness testing. To wrap up, here is the summary videos.
The next spotlight talk will be Ambient Diffusion Policy, Imitation Learning from Suboptimal Data in Robotics by Adam Wei and co-authors. Online, Adam, welcome.
Hello, thanks for having me. Can you hear me?
Yes.
Okay, great. All right, can I go ahead and get started then?
Yes.
Okay, great. All right, so my name is Adam. I'm a PhD student working at MIT with Professor Russ Tedrick. And today I'll be presenting our work on ambient diffusion policy. So ambient diffusion policy is a way to do imitation learning from suboptimal data in robotics. I know this workshop is mostly focusing on high quality data, but in this talk, we're really looking at the lowest quality data and seeing how we can still train really good policies from this low quality data. Also, obviously, I'm not here, but my collaborator, Thomas Cohn, should be somewhere around, and he'll be running the poster session. So please ask him any questions. He's great. All right, so in robotics, a standard thing to do is to collect a small but high quality data set for your target task. And we'll call this in-distribution data. But at the same time, there's all this internet data out there that's very vast. But a lot of this data has some type of distribution shift or suboptimality. For instance, it could be from non-expert teleop, it could have embodiment gap, task level mismatch, or many other issues with this data. In this talk, when I say suboptimal data, I really mean any data that's not our target high quality in distribution data. So the standard approach in machine learning and also in robotics today is often to just discard this data. But this is wasteful because there's still value and utility in out of distribution data. We just aren't using it correctly. So let's take a look at a quick case study. OpenX is a massive collection of robot data that currently has 72 different data sets. But anyone that's used this knows that it's generally low quality. So for example, OpenVLA actually only uses 27 of the data sets in OpenX. So what happens when you add in the rest of the data sets? We find that with naive co-training, the performance plateaus. But with our method, we can continue to extract a useful learning signal from the low quality data. So concretely, we're looking for principled algorithms for learning from suboptimal data. We'll be using the color orange for the in-distribution data and the color blue for the suboptimal data. All right, so how does our method work? Well, first consider the diffusion time axis. The goal of diffusion policy is to use your high quality data to train denoisers at all the different noise levels. Now let's say I give you a bunch of suboptimal data. The common approach is to co-train on both, but with dataset reweighting. And so this is done in a bunch of places. But this, we argue, is fundamentally the wrong objective because you're still teaching your model to learn both the good and the bad parts of your suboptimal data. Instead, in our method, we advocate for noise-dependent data usage. And basically, this allows us to selectively learn the good parts of suboptimal data while ignoring the bad parts. So concretely, we argue that suboptimal data can be used along two intervals. The first interval is at high noise levels. So why is this true? Well, at low noise, a suboptimal action and a high quality action might look very different. But as you add in more noise, they become looking more and more similar. And so it's actually theoretically grounded to use low quality data at higher noise levels because the distributions are more similar. The second interval we identified is to use low quality data or out of distribution data at low noise levels where denoisers have a property known as locality. Intuitively, this means that at low noise, a diffusion policy is learning local motion primitives instead of the global structure of the action. So this means that you might have a trajectory that's collected for a completely different task, but you can still learn the useful local motion primitives by training with this data at the lower noise levels. So in the paper, we give pretty precise and theoretical interpretations of both of these intervals. And we also provide an automated procedure for annotating where these intervals are for different types of data sources. Our paper also provides an alternative interpretation of the algorithm. So we essentially analyzed the structure of robot data, and we identified that feature learning in diffusion is actually noise level dependent. So because featured learning is noise level dependent, then data usage should also be noise level dependent. And you can get more details about this by talking with Tommy, or you can check out the paper. But essentially, we're only using the suboptimal data at the noise levels where its features align with the high quality data. Okay, great. So let's talk about some of the experiments. The first experiment we did was to try to do a task in lab very well with a small amount of data, but instead learn with a lot of suboptimal data, for instance, from OpenX. This is an interesting data set because it's very heterogeneous, it's very unstructured, and it contains all sorts of different types of distribution shifts. We evaluated this on two different tasks. The first is tower building, where you try to build this tower in like a Jenga style. And the second is table cleaning, where we try to, okay, the video is not playing, but we try to put these objects away into the drawer. So here are the results. In all of these plots, the blue bars represent two variations of our ambient algorithm, and the green bar represents the code training baseline, and the gray bar is the data filtering baseline. This is what happens if you don't use any of the suboptimal data. The first thing you'll notice is that the ambient policies build 33% taller towers than code training, and 84% taller towers than just data filtering. Now let's take a look at the table cleaning results. You'll notice the same trend where the ambient policies are just much better at extracting useful signal from suboptimal data. And in fact, we did an interesting experiment where we took Magic Soup, which is a smaller high quality subset of OpenX, and expanded it to contain more data in this like custom OXE mixture. And we find that as you scale up the amount of suboptimal data from OpenX, Ambient's performance continues to scale, whereas co-training, shown in green, clearly plateaus. So these are two major benefits of Ambient. It's just better at using the suboptimal data, and it scales better when we add in more. Another benefit is that Ambient works on arbitrary sources of suboptimal data. So to illustrate this, we actually explored three different types of three different ways your data could be suboptimal, such as low quality teleop, simulation data, or maybe task mismatch. And we find consistently across the board that our method applies and it beats the co-training baseline. All right, so basically in this talk, I went quickly over our new algorithm called Ambient Diffusion policy, which essentially argues that suboptimal data should only be used at specific noise levels along the diffusion process. And it's a principled method with theoretical backing that also works on arbitrary suboptimal data sources in robotics. We actually did tons of experiments, and I really think this is a pretty promising idea that I'm currently trying to scale up at my internship. And so if you're interested in learning more, I would encourage you to check out the project QR code or talk to Tommy at the poster session. My email inbox is also open in case anyone has offline questions afterwards. Thank you for everyone's attention, and I'm happy to take any questions about our new method.
Thank you, Adam. We do have time for one, maybe two quick questions.
Okay.
If anyone has a question here. Ooh.
I have a quick question.
Yep.
About kind of the data, how you select which is and which isn't.
Yep.
Like the good part. Any tips in like practical terms?
Yeah, okay, so that is a pretty important question underlying this framework. So this framework is agnostic to how you split up your data set. And then once you split it up, it just works. But you're right that we first need to figure out how to split the data. So one natural way that we explored in this paper is you collect data in-house that you consider high quality, and then that's your high quality data, and everything else that you consider suboptimal. So that's one way to go about it. This is really good if you want to train a policy that's very good at your specific task. But let's say you're a company that's trying to maybe train a generalist policy. Well, then you need some notion of quality that lets you pick the highest quality data between all the different tasks. And I would say that's more of an open problem still. But as that improves, so will basically our algorithm.
All right, thank you very much. Let's give a hand.
All right, everyone. It's great to see lively discussions at the posters. Thanks everybody who submitted a paper and a poster and presented it today. That's really great to see. And thanks everybody for coming by our workshop. So please stick around for the next couple hours. And we still have a good program ahead of us. So it's my great pleasure to introduce Dana Kulić. She's a professor at Monash down in Melbourne at the southern tip of the continent and country. She's the founding director of the Robotics Center at Monash. She's an ARC, Australian Research Council Future Fellow, and she's also deputy director of an industry transformation training center for optimal aging, where she's exploring how robots can help us with aged care. Dana's very interested in robots, how robots can learn with and from humans and how they can work with humans safely and productively. She's exploring a lot of human-robot interaction in this sense, and I'm looking forward to her talk on assessing and improving demonstrations and the demonstrators. Thanks, Dana, for being here today.
Thanks so much, Nico, for the kind introduction, and thanks to all the organizers for organizing this workshop and inviting me to participate. So I was very keen to participate when I saw the title of the workshop, because I think this question of the demos is one of the kind of underexplored and underappreciated topics in imitation learning. And what I hope to talk about today is both about how we think about demonstrations, but also the people that are actually providing those demonstrations. So let's look at the typical learning from demonstration pipeline. So I probably don't need to introduce this to you because I'm preaching to the choir here, but I just want to kind of review it just so that, and I'll kind of pick out a couple of things that I think are very interesting. So typically what we have is some kind of demonstrator, a human teacher, and they are providing demonstrations through some kind of teaching interface. And then we collect a bunch of those demonstrations into some data set, and then we use that data set. We instantiate some learning algorithm, and we want to learn the policy that will allow the robot to then execute execute that task. And I think most existing work kind of follows this sequential pathway. So first you collect the data, you form your data set, and then you do the learning and the execution afterwards. So we've seen a lot of interesting work on what should be this like teaching interface. So how do we collect these demonstrations? And there's been quite a diversity of possible interfaces. So we've seen these kinds of systems where we have the person is demonstrating the task with their own arm, but using the end effector that's equivalent to the end effector that the robot will have. Then we've seen these kinds of systems where you kind of have a leader-follower type framework where basically the human is operating the exact same kind of hardware that the robot is, and just a kind of like a mirrored system. And then we've also seen these kinds of systems where we have kind of like a VR type system where the person is viewing what the robot is viewing, and then generating the motion with their own arm, something different than what the robot is doing. So why do we have this kind of diversity of interfaces? So let's kind of think about what makes a good interface. And I think there is a kind of possibly a trade-off, because what's good for the demonstrator may not be what's best for the robot. So if we think about from the demonstrator's point of view, I would prefer to just do it with my own body the way I normally would. In fact, I wouldn't want to be attached to any sensors or having to operate this kind of unwieldy teleoperation interface. I prefer no physical encumberment. So of course we could do that. We could just collect video or some kind of unobtrusive sensing of the from the demonstrator. But the problem is that if we just let the person go and do it themselves, there's no guarantee that that demonstration is actually achievable by the robot, because the embodiment of the demonstrator and the robot may not be the same. And so if I just let the person do it with their own body, then I need to figure out how to map from the human action to the robot action. So what's best for the robot is show me in the robot's body the way the robot would do it. I offload the problem of this mapping from the human embodiment to the robot embodiment to the demonstrator. Now, I also want to make sure that the robot has the same observations as the demonstrator, because what I don't want is if the demonstrator has access to some information, for example, if the demonstrator can hear a click and that's when they know to stop pushing, but the robot doesn't have a microphone, then the robot is not going to be able to successfully replicate that demonstration. So if I force the demonstrator to only have access to the information that the robot has and to show me the action only in the action space that the robot has, this is perfect for the robot. The problem is that this is obviously harder on the demonstrator, and it kind of violates a central assumption that we have, which is that the demonstrator knows the best way to do the job. Because once I've forced the demonstrator to have this kind of, maybe unnatural viewpoint and using these unnatural kinematics that they're not used to, then maybe I'm not so sure that they actually know what the best way is to accomplish the task anymore. So now let's say somehow we've collected our bunch of demonstrations. Now we do task learning. And there's also been a lot of really cool activity in this domain, especially recently with these vision language action models. And all these systems are kind of following this exact same pipeline. But so I'm not going to actually talk at all about what are the task learning methods. What I find interesting is what's happening in the demonstrations. So demonstration data is not just collected, it is also curated. So somehow you collect a whole bunch of this data, but then you kind of select some subset of it. And I really enjoy, this was the Pi Zero paper, where they kind of encapsulated what's happening very nicely. So they say, this is our pre-training mixture. We have a subset of the OXE and a subset of the Pi data set. We use a subset of OXE, which is the magic soup. And so it's kind of like somehow, they're very open about this. They take a little bit of this and a little bit of that, and then they stir it together. And then there's the magic soup of the right data set, and that's what we used for learning. So I thought that was really interesting because I'm like, well, what makes the soup so good? Like, how much salt do I add? What are the ingredients? And they kind of left this underexplored in the paper. So what makes a good demonstration? And I'm actually going to flip that and ask what actually makes a good teacher. So I think there's kind of two ingredients. One is the distribution of the demonstrations. So if we have a demonstrator who is always showing me how to do the task in only one way from only one part of the state space, I don't know what to do when things in the environment change. So I want this kind of diversity across the relevant state space that will help me to know what to do if kind of context changes. And then for each individual demo, I would like to know that this is a good demo. So if I have, if the person is like unsure, if they are, if the demo is partially successful or suboptimal, this will also degrade the subsequent policy. But the problem is that, I'm trying to learn how to do this task. So I don't know what the task is. So how can I know if the demonstration is good if I don't know what the task is? So this is, I think, a super interesting question is how can we assess quality, right? So one thing that we can do is we can, kind of collect a bunch of data, train a policy, and then look at that policy and say, okay, is this good or not? But hopefully we can do something even before we learn. That would be kind of the ideal case. Okay, so let's look first at this first question. Can we help the teacher give us better distribution of demonstrations? So the idea here is, what if we break this sequential nature of the chain? What if we actually allow the demonstrator to see what how their demonstrations influence what the robot is learning? So the idea is that we collect some subset of data from a demonstrator, and then we show them this is what the robot can do based on what you've shown us so far. So we convey the robot's current capability by kind of rolling out example trajectories. And then we say to the person, okay, given what you've seen of the robot's capability so far, you give us the next demonstration. It turns out this makes a huge difference to performance. So what I'm showing here is the blue is the no access to feedback. Now what EF and NF stands for. So the blue is access to feedback, and the NF is no access to feedback. And what you can see is that by just showing the demonstrator what the robot can do so far, it actually helps them to distribute their demonstrations much more effectively, which improves both robot performance and the number of demonstrations that are required. Now, another thing that we can do is we can show the demonstrator. So again, we do a kind of interactive learning and demonstration collection where we show the participant with a kind of heat map visualization, or with a selecting the place where we're most uncertain. We visualize to them where the robot is uncertain if it could accomplish the task, and then we ask them to provide subsequent demonstrations. And again, we show that this significantly improves the efficiency. So the number of demonstrations we need to successfully solve the task across the entire state space. But even more interestingly, if we then ask that same demonstrator to show us on another task, they transfer that learning. So they kind of understand better, oh, I need to distribute the demonstrations across the space. And so then what we see here in the transfer test, the performance is much better than in the baseline. So even just kind of this very we can even think about these as a training task that allows us to better train the demonstrator about what kind of diversity of demonstrations is useful for the robot. Now let's look at the other question, which is for each individual demonstration, how can we assess the quality of that demonstration? So one approach is kind of like the obvious one, is a good demonstration allows us to do good at the task, right? So allows us to improve task performance. So what we do is, we collect our demonstrations, we train our model, and then we evaluate on the task, did we, achieve success or not? And if we achieved good success, we say, yeah, these are high quality demonstrations. If we didn't achieve success, we say these are low quality demonstrations. And our hope then is that, if we can reproduce the success on the trained region of the state space, that this will then help us to also generalize to the rest of the state space. So this works, but it's kind of annoying because we need to basically, for every set of demonstrations, we need to train the model to evaluate it, and then see if, and then also we're kind of still making this assumption that it's going to generalize, which may not be the case. So one thing that we've been interesting in is thinking about whether we can look at some task agnostic metrics that can tell us whether a trajectory is a good demo even before we do any training. And of course, it turns out that, we do have some prior knowledge, from kind of classical robotics that tells us what are likely to be good trajectories. So things like manipulability, distance to joint limits, the path length, all of these metrics are ones where we can hypothesize that a good demonstrator is likely, not to operate the robot too close to the joint limits, not to have, to minimize the path length when achieving the task, and so on. So we wanted to see whether we could use these task metrics to help us to kind of down select good data for training before training takes place. So what we did is we had this kind of challenging to train kinesthetic teaching task that you see here. And we recruited a bunch of participants to give us demonstrations with diverse levels of expertise. And then we computed these metrics, so path length, jerk, manipulability, and so on. And then we kind of wanted to look like, can we look at these features of the trajectories and cluster them into, so what we wanted to look at is, of course, for each task, the actual path length is different. So I can't just look at path length as a metric, but what we wanted to look at is the consistency. So how consistent is that feature? And so what we see is if we separate into just these two clusters, we see that consistent demonstrations actually are consistent across all or most of these metrics, while the inconsistent demonstrations are much more inconsistent, so high range with a wider distribution across all the metrics. And if you just choose the consistent ones, you get much better task performance when you subsequently use that data for training. So we think this kind of simple consistency metrics can be used in a kind of task agnostic way to assess demonstration quality. Now, what happens if you find that one of your demonstrators is not giving you good demonstrations? So I think the current approach is we just throw their data away and forget about them. But if we want to move towards actually, collecting demonstrations from end users, we might also want to think, well, can we help them to become better demonstrators? So how can we actually help demonstrators improve their teaching? So we were thinking about how can we do training to help demonstrators improve by having access to expert skills without requiring an in-person expert to help them train. The pipeline that we were investigating is we have an expert demonstrator, and we have some data from that expert teaching a robot, from expert demonstrations. So now we can have that data in different forms, right? We can have video, and we can show that video to a novice teacher, and this is observational training. And so the novice teacher looks at the video of the expert, and then after observing those videos, then they try to teach the robot themselves. This is kind of standard. Most of us, when we're being trained, we're watching some videos online. Now, we also have the actual trajectory data from that demonstrator. So we can also do kinesthetic training. This is also known as hand-over-hand training. So a good example is, when a parent is teaching a child how to handwrite, can put the hand over and kind of guide them. So we can do this with the robot by asking the person to just put their hands passively on the robot and just observe while we replay the expert data. So now we have kinesthetic training, and then we observe how that user then teaches the robot. And then we also, so in addition to the two observational and kinesthetic training, we also looked at discovery training, where we just let the person explore the robot, try it out, and see if, see how the robot behaves, what it does, kind of like a free-for-all approach. And we wanted to see how these training approaches would influence demonstration quality. So what we did is we trained them on one task, and then we asked them to provide demonstrations first on that same task, and then to a different task. So the baseline is the kinds of demonstrations they provided before any training. The retention is after training on the training task, and the transfer is after training on a new task. And so what we see is that all training is good. So regardless of the type of training is useful because it will improve the demonstrator performance. And what's also really interesting is that the training, people are very good at generalizing. They will retain what they have learned to the transfer test. Now, kinesthetic training is the fastest, but I think the takeaway message is any kind of training, providing training and feedback to the user is really helpful. So I'll close here, and I want to just close with a couple of final thoughts. So if we think about how to improve demonstrations, we want to think about how can we improve demonstration diversity by providing better interfaces and better instructions and feedback to teachers. And similarly for demonstration quality, I think having better metrics to allow us to provide that feedback would be really valuable. But I think the other part that is really underexplored is actually improving the demonstration and teaching experience. So at the moment, this is extremely tedious. And I think we could do a lot more to improve so the feedback and the assessment that I've been talking about, but also to make the process of teaching a lot more enjoyable and rewarding for the teacher. So I'd like to close by thanking all my students, collaborators, and sponsors, and thank you for listening. I'm happy to take any questions. Yeah, so that's a great question. So my feeling from us having run these experiments is that people are actually really good at, like once kind of they get it, then it generalizes really well. So I would say the answer to that question depends on where they are in their kind of teaching expertise, like, where they are along that path. I think if they are novices, it's really important to give very frequent feedback. But as they become more experienced, then I think the only, then you can really tone it down on the amount of feedback, give it less frequently, and maybe only if things are different than what they're used to, then you want to give early feedback. Yeah, so that's a great question, is when you have somebody who is, so maybe you've already trained the policy with tons of demonstrations that are all of a very high quality, but now somebody wants to change, to change how that policy is performed based on their personal preferences. So I think this is where you really want to get into this kind of interactive learning, where you adjust the policy a little bit based on their feedback, and then let them provide corrections. And I think also exploring not just demonstration-based feedback, but also corrections, preferences, as well as demonstration, I think is really valuable in those contexts. And I think also providing training to those novice users would also be really helpful. So before you ask them to give demonstrations or feedback on the tasks that they care about, just give them, a sandbox environment where they can just get a little bit of experience and confidence as well. Because one thing that I will say, I didn't mention it in our results here, but what we also notice is a big difference between perceived expertise and actual demonstration quality. So we always, when we're running these experiments, we ask participants to self-assess their expertise. And then, of course, we're measuring, when we collect their data, we measure, our demonstration quality metrics, as well as how good is it at training the policy. And we often find that there is a mismatch between the perceived expertise and the actual quality. And so I think sometimes with novice users, they will, it's about their own, they don't have a way to assess themselves. So I think having that toy box environment where they can build a better understanding of what the task is and their own capability on the task, I think would be really valuable. Yeah, that's a great question, right? So, I mean, pretty much the entire learning from demonstration approach kind of assumes that the human is the expert, right? Like we're just trying to copy them. But there are differences. So you can kind of also think about, what am I going to copy, right? Am I going to copy the joint level trajectory? Or maybe, a lot of work is just copying the end effector trajectory and then kind of have some other low-level controller that's figuring out the torque distribution in the joints and exactly how to do the joints. But that's a little bit dangerous, right? Because then you're assuming that the person only cares about the end effector trajectory, which may be true for some tasks, but may also not be true. So I think this is a really good question. So of course there are also works that are looking at a kind of combination of imitation learning and reinforcement learning, where you say, okay, I want to stay as close as possible to the distribution of the demonstrations, but at the same time, I also care about torque minimization and other things that the demonstrator, doesn't have good visibility into. Okay, so the first question was usability. Oh, legibility. Okay, so actually, when we were coming up with these metrics of what do we think these kind of like task agnostic metrics could be, we had a big debate about legibility. So we used the Anka Dragan's definition of legibility, which is about kind of how early in the trajectory you're communicating your final intent. But we had a big debate because I was like, I don't know if the demonstrators would care about this. I think it depends on the framing of what, if they think, okay, the robot is going to be doing this in front of other people, then I need to care about legibility. But if I think like I'm showing this robot, how to do this task, and then when I'm done showing it, it will just do it on its own, then they would not care about legibility. And so we did include it. But it was not the, if you look at all the metrics, it was one where we had the largest range of consistency, because exactly for this reason, because I think it depends on the framing. Like the demonstrator will only care about legibility if they think that the robot is going to be doing this, in front of another person. Your second question is around, you're absolutely right. Like these are not task metrics, right? But the reason why I don't want task metrics is because if I don't actually know what the task metrics are, right? Like, of course, when I set up these toy examples, of course I know what the task metric is, but when I'm actually learning from the demonstrator, I don't know what the task metric is, right? That's what I'm trying, I'm trying to avoid having to learn the reward by just simply copying the policy of the demonstrator, right? So that's exactly why I want task agnostic metrics. I think that's one approach, but I think it's risky because if you have these like partially successful or suboptimal trajectories in your initial training set, it will actually degrade your task performance if you just include everything in your training set. And I think that's exactly why we see this magic soup type approaches because certain things are being excluded because they are found to be degrading the overall task success. Yeah, so this we did this with like a very simple toy domain so that we could do exactly this, which becomes completely unrealistic when we're thinking about more sophisticated policy. So I think this is a really good, actually unsolved question: is how do I provide this feedback about the state space coverage when the state space becomes very much. So if you're a PhD student, this is a really cool topic to to look at. Great, thank you. Okay, thank you.
All right, so we'll move on now to more spotlight talks. First, we'll have From Action Labels to Sets, Rethinking Action Supervision from Imitation Learning from Corrective Feedback by Zhaoting Li and co-authors.
Hello, everyone. Sorry about the press. I'm Zhaoting, and I'm from a PhD candidate from TU Delft, and one of my colleagues, Rodrigo, is also here today. And so I'm happy to present the work From Action Labels to Sets, Rethinking Action Supervision for Learning from Corrective Feedback. We consider the interactive imitation learning. The robot takes an action under its current policy, and if the action is suboptimal, a human teacher provides some corrective feedback to guide the robot to improve. However, in the real world, the teacher feedback is not guaranteed to be optimal. It might be noisy, relative, indicating only a direction of improvement. Okay, so how it works in two-dimensional action space, and we can provide this corrective feedback. The standard approach to learn from this type of feedback is behavior cloning, that directly imitate the teacher action. This works for clean data, but it can overfit some suboptimal data with some expressive models like implicit behavior cloning or diffusion policies. There are some existing methods try to address this by relaxed assumption of behavior cloning to some pairwise comparisons. Like in this preference-based learning, that they only assume the positive teacher action is better than the robot negative action. But the problem is that this assumption is a little bit weak, and the resulting policy is a little bit under constraint and can output a lot of suboptimal false positive action inside this green boundary. So this gave us a key gap. We need a supervision that is more robust than point-wise behavior cloning, but also more informative than pairwise preference learning. And our solution is set value supervision. We convert a correction signal into a desired action set. This set is assumed to include the optimal action. So the learning target becomes of, instead of imitate these action labels, we try to place some probability mass into this desired action set. With this perspective, even with noisy action labels, we can recover the optimal behavior quite well. And I will show the detail of this method. So first, let me introduce the desired action set. This is a key concept of our method. And for one correction, we can define a set of possible actions and a set of actions that could be the optimal. So it for some correction feedback, like relative correction, we can specify a half space, and we could make it more informative by defining some positive desired space. If we know this correction is some absolute correction, like human intervention or demonstration, we could make the set more specific, like a ball around this human demonstration. So let's take this positive set as example. A single set may still contain some suboptimal actions. Like if we specify this set, there are also some suboptimal action here. What we did here is that we can aggregate more corrections to refine this set. So what we have is have a human teacher to provide this correction and refine this set iteratively. The next, we train the policy using these desired action sets. The objective is to increase the probability that the policy sample action from these desired sets. In other words, just push the policy distribution into these sets. The way we achieve this by defining a target distribution, where the current policy is weighted by how the action is consistent by the desired set, which is denoted by that gray shaded equation. We then use KL divergence to calculate the loss and update the policy. And this KL loss can be rearranged into weighted behavior cloning and compare with this behavior cloning objective, which is in the red or orange color, that the learning signal is no longer concentrated on one possible noisy label. So it's distributed over the entire desired action set, and that is what makes click robust to noisy actions and avoid overfitting. Let's put everything together. So first we have a desired action set, and then we update the policy accordingly. The policy not perfect yet. We can receive more corrections from the human teacher, and iteratively the policy can be improved. We test click with several baselines across different feedback types. The main result that it remains competitive with behavior cloning baselines, even the feedback is accurate. And when we consider some other types of feedback, like some Gaussian noise feedback, relative feedback, or directional feedback, the performance of click is also quite robust, but all other baselines, the performance drops. And we test the click method in 3 real robot experiment tasks. In this ball catching task, click handles partial feedback, where the feedback is provided either to the opening of the gripper or the position of this end effector. In this water pulling task, the robot must control the position and orientation of the robot, and we use absolute correction in the early stage of this task and fine-tune the precision of this pose using relative correction feedback. In the inserted task, the robot needs to push this T-shaped object into the U-shaped ones. It's a long horizon task with multiple different solutions, and click can also successfully learn from this task, and it outperforms diffusion policy and implicit behavior cloning. This experiment shows that the method works beyond the simulation and can handle different types of correction feedbacks in real world. And finally, there's a follow-up work that extends click into diffusion policy and action chunk space. And we found that it can set value supervision also can result in a higher quality data set during online data aggregation. So if you are interested, you can go to the poster, the paper session tomorrow if you are interested. To conclude, behavior cloning is a little bit strict, and preference learning is a bit weak. So our set value supervision provides the middle ground, and as a result, it remains robust to noisy actions and can create some high quality data set during data aggregation. That's all. Thanks for your attention. the data is collected using some space miles, and it's similar to demonstrations, but instead of teleoperating the robot for the whole time, we let the robot to deploy its own policy, and if it performs not really good, we can take over with the space miles, and at that time, we can have the positive action during the teleoperation, and also the negative robot action that trigger this intervention.
Hello everyone, very excited to share our new work, RoboPocket, improve robot policies instantly with your phone. We use the sensing, communication, computation, and display features already available on iPhone to collect the robot data, and more importantly, to perform online dagger without any real robots. Robot-free systems like Wumi greatly expand where demonstrations can be collected. However, their feedback loop is still offline. The users collect the data first and then upload the data, and then run ORB SLAM and Gripper's data estimation, and only then get a conclusion whether a trajectory is valid or useful. And post-training has a similar delay. Deploying a robot, inspect failures, collect another batch of data, and then retrain the policy. If the ORB SLAM tracking fails or the policy fails in a specific state, that information arrives too late. So the bottleneck is not only hardware cost, it is delayed feedback on both data quality and policy behavior. Here, I would like to distinguish two related but very different problems. The first one is off-policy data collection. The goal of policy collection is to improve data availability. We want to collect more demonstrations in more environments with more objects at lower cost. And the second one is on-policy post-training. The goal of on-policy post-training is different. It is not only about collecting more data, it's about collecting the most useful data for the current policy. So the central question becomes, how can we collect the data within maximum efficiency? So RoboPocket closes the data quality loop with three integrated features. The first one is a 3D printed gripper, which only costs $70, and there's no morphology gap between it and a robotic gripper, so the actions can be naturally mapped to the robot motion in Cartesian space. And the P2P communication synchronizes the timestamps and coordinate frames across two iPhones. So this enables bimanual data collection without a separate workstation. So finally, the iPhone displays tracking quality, trajectories, and motion warnings when users are collecting data. These features make low-cost demonstration immediately verifiable, instead of moving the cost from collection to data filtering. So now we move from collecting data to policy improvement. So RoboPocket previews the policy's predicted actions by augmented reality without deploying the real robot. In this RGB sorting example, the policy moves towards the run block. The user identifies the failure, stops the inference, and records the correct motion from that state. After the update, the next rollout follows the correct order. So the key in this scenario is that new data is selected by the policy's current weakness, so we can improve the policy with a very on-policy manner. So we collect a targeted correction as a failure rather than blindly collecting more data. To support this interaction in real time, RoboPocket uses a Cloud Edge framework. The iPhone uploads the current observation to the inference server, which returns an action trunk in about 150 milliseconds. And the phone handles the AR rendering and multi-device synchronization locally. When the user records the correction data, the trajectory is uploaded to the data serving node and added to the online dataset. The training server samples from both offline demonstrations and online replay buffer containing new correction data, and continuously updates the policy and broadcasts the latest checkpoint back to the inference servers. So this asynchronous system keeps the inference responsive and completed the policy update cycle within about 1 minute. Yeah, here is the block sorting behavior. So this is a block sorting task. The behavior cloning policy reaches for the wrong block, while the policy after instant policy iteration follows the right RGB order. So please look at these two videos. This makes the benefit concrete. Our targeted correction data is able to fix the task level failure immediately from the robot-free human intervention. And the same pattern appears beyond the first block sorting task. We can have a look at these two tasks. The seasoning proving recovers from distributional shift problems, and the snack bagging task demonstrates the performance on long horizon tasks. Here are the quantitative results. We compare our method against the naive behavior cloning with more data, and some other Dagger baselines with different Dagger systems. In block sorting, especially we can find that the 50 targeted correction trajectories can outperform the imitation learning baseline trained with even 300 trajectories. And across four tasks, a small amount of targeted correction online data produce very strong improvements. So in recent years, especially for the robot learning community, almost everyone is working hard on offline data collection because we think it is essential for policy pre-training. But once failures are visible, like what we are doing in this system, we can visualize the policy failures with AR techniques. And we can make the targeted corrections, and these targeted corrections will provide much more value. And in conclusion, RoboPocket turns the iPhone from a passive recorder into an interface for continuous policy improvement. It provides low-cost data quality verification, online policy iteration, and closes the policy update loop in about 1 minute. And the broader message is simple. The deployment should not be the end of the robot learning. It should generate the next batch of useful data. And thank you very much for watching.
That was the Spotlight Talks, and we have one more speaker coming up, Dr. David Watkins. He's a robotic researcher and engineer working on the intersection of robotic manipulation, learning, and data infrastructure. And he recently joined Tutor Intelligent as their research lead, following several years at the Boston Dynamics AI Institute. And what made him leave that and go here? Hopefully we learn that in the upcoming talk.
Thank you very much. Thank you all for attending my talk today, where I'm going to talk about both. Oh, I thought I shared the screen. That's being shared.
Okay.
Yeah, all good. Okay, where I'm going to talk about some of the work I've done previously at Ray and some of the cool new work that we're doing at Tutor. And I'm going to start by talking about some stuff that a lot of the different presenters here have talked about so far, which is Yumi-style demonstrations. And so I'm going to talk about how we can get smooth quality data from very few demonstrations just using Yumi-style alone. So we've sort of beat this over the head quite a few times, but the basic premise is that we can print very inexpensive data collection interfaces and get surprisingly robust generalizable behavior because we're doing a relative position control of the policy using data just from the perspective of the camera. And so we can perturb the scene
and get this repetitive behavior over and over again. That's quite reliable with only something like 1,500 demonstrations in the case of this cup in the wild task that works across lots of different places. So this is work from Stanford, the original Yumi paper, and the inspiration for a lot of the work that we ended up doing at Ray. And so at Ray, I built a team of people that focused on every aspect of this problem, all the way from designing the fundamental hardware to doing data collection ourselves, processing the data, training policies, and deploying them on robot for more sophisticated behavior. And a common theme in all of the different talks we've seen today is that loss is not a good indicator of performance. A good policy and a bad policy will have pretty much the same loss curves. These policies are very good at learning whatever it is we throw at them, even if it's not very good data. And there's really also no free lunches in data collection. So we want the ability to scale and we want to reduce the embodiment gap. But things like human hands are very far away from the embodiment of what a robot can do versus, this teleoperated data might be very difficult to scale up because we need so many robots in order to do that. And we want to push the boundary in both directions. So one of the first things that we started doing at Ray is we took the original Yumi formulation and wanted to make it more ergonomic. We wanted a lot of people to very easily pick this up. So we moved away from the rack and pinion 3D printed mechanism and moved to a multi-bar linkage mechanism shown on the right. And that was significantly better for improving the quality of data just because we had something smoother that people could use that traveled much more easily. It just meant that the demonstration quality was going to be higher. And we were going to look at this empirically from all directions. And so you can see here that we also redid the trigger mechanism itself, which just made it very easy for people to use and manipulate. We also looked at other kinds of form factors. Ray Institute had quite a few spot robots around the Institute. I think we had something like 26. And so we wanted the ability to program behavior on one of those robots as well. So we designed a Yumi-style gripper for the spot end effector, which was this clamp-style gripper. And we even experimented with different ways we could collect data. Something we noticed is that the spot had very specific types of behavior it could execute. So this is one of the researchers at Ray collecting data like a spot. And so you can see he's being very deliberate about the directions by which he's grabbing things and picking things up. And it was quite entertaining to sort of have this robot-like human behavior. See very, very pointed movements. And so we wanted to find smarter ways to compare the kinds of data that we were collecting. And so on the left is us deploying the Yumi cup in the wild data set on our robot in our own environment. And on the right is our initial attempt at collecting some demonstration data of our own and getting significantly worse results. And so we wanted to explore what is the difference in how we're collecting data versus how they collected it. One thing we looked at was episode length. How many actual steps, how many data points are we collecting? And we noticed that not only was ours on average longer, but we had a significantly narrower distribution of episode lengths when compared to Stanford's data. So they had a longer tail in the sort of upper bounds of maybe mistakes that the data collectors were able to do. We also noticed that the Stanford data included faster movements, that they were more sudden, a higher jerk, which meant that they were not being deliberate and careful when collecting data. They made sure that the maps that they were collecting to get good localization performance still worked in faster movement regimes. We also looked at the relative trajectory shapes and paths and noticed that our trajectory shapes were significantly easier to learn because there was significantly less diversity. We were being very consistent in how we collected data, which was sort of counterintuitive to us. That instead of being very careful and deliberate, it was almost better to have this diverse set of different explorations. And then finally, we just did PCA to see if we collapse as much of our data into a point, how does it perform and look versus Stanford's? And you can see that in red, our data is quite homogeneous, that we want to sample from more of the distribution of potential trajectories that still end up solving the problem in order to get a better representation of what those behaviors are. And so our key takeaways in sort of this initial analysis was that the Stanford Cup in the Wild data set was offering a much higher spatial diversity that had shorter, more aggressive trajectories and was more difficult for the model to predict smoothly versus ours, which were very clustered in how the behavior was going to be executed, that they were longer and smoother trajectories and had more dynamic gripper usage. And so using some of that data, we were able to collect better demonstrations to train a policy. So this is us with a Robotique gripper now that we collected some demonstration data for. We collected 1,024 demonstrations and wheeled the robot into a place that we'd never collected data for. I was able to do this on a cup that was within the distribution. And then we wanted to show again that this would work on a different color cup in a different part of the same environment. Again, it's not seen before. I was able to do it, which was good. Some of the lessons that we took away were working. And then we also wanted to see, could it work on different planar surfaces? And so we were able to demonstrate that as well, that the policies still were robust to these perturbations in the environment. And this was all work that we were doing in late 2024 as we were analyzing things to figure out sort of how far we could push these policies before they would start breaking as we collect sort of low data regime data. And so this is us testing in an even more cluttered environment. Of course, we end up breaking the plate because we just didn't collect enough data. So we wanted to go and deal with more challenging tasks. So this is bottle pour. This is pouring out granulated media into a mug from a clear translucent cup, which I will explain in a second why that's really important. But we were collecting thousands of these demonstrations around the Institute from all kinds of different locations, enough to train a policy. But one of the important things here is that these policies are Markovian. They rely on us having a very stable input and output definition for any particular step in this. They're also memoryless. So because this is a clear translucent bottle, the policy is aware that it is done. But if I switch this out for an opaque bottle, the policy is not able to actually perform the task again. So we had to be very thoughtful about how we curated this data. Where are these sources of data and how are we making sure that they still behave in a Markovian way? So we came up with this sort of mental model for different ways we could collect data. We had thousands of hours of pre-training data. This might be various levels of quality. We now have as a sort of field this luxury of data available on the internet for all of us to be pre-training with. And then we considered sort of this middle tier of demonstration data that we know are high quality, that we know are behaving the way we want to, that there's no ambiguity, that there's no lost frames, that the data collector is always doing the right thing, but maybe is not exactly what I want to deploy on the robot. And so that's going to be sort of my mid-training data is a term that's being thrown around a lot. And then finally, the fine-tuning data, which is very few numbers of hours of data that we need to get the exact behavior that we want deployed onto the robot. And so this is me, Christmas of last year with two of the Yumi grippers. I call this Edward Yumi hands. And so what I was doing is I was going around and opening up all of my Christmas presents, collecting not only the RGB information, but also all of the tracking, force interaction data of opening presents. And what I realized as I was going through the data that I ended up collecting on Christmas Day while my parents were being incredibly patient as I was collecting all of this data was that there's a lot of things that we don't end up doing when we're curating demonstrations that we do out in the wild. That if I can encumber myself with these grippers, I will be creative and solve problems that I would never end up seeing in a very well-organized data set that I collect of over and over again, picking and placing cubes or cups or things that we as researchers are so biased to try to collect and demonstrate the research that we're doing. And that's going to limit the ability for these policies to adapt to a variety of different conditions that we care about down the line. So one of the things that we have recently shared out with the world is this bridging data collection procedure. And so what we do is we collect a base data set of demonstrations using Yumi. We train a base policy. We evaluate that base policy to find any holes or any lack of coverage in that behavior that we care about. And we train a router to, then we collect a support data set using teleoperation for the hard parts that we notice that the policy is not able to do well. And we train a router to differentiate between those two different steps as a conditioning variable for the policy itself so that we can get better behavior. And we actually modified the diffusion policy architecture to better attend to the different parts of the robot. We noticed that when we just pass in state alongside images, that the policy is more likely to attend to the state and memorize the actions based on that rather than properly attend to the visual input alone. And so what we ended up doing is cross-attending with the state to get a better representation of the scene that we care about so that we can solve the problem in a more disambiguated way. And in doing this, we can get more sophisticated behavior. There's more videos that I would love to show here, but simply not enough time. On the project webpage, feel free to search for this paper online. But this part of the task where the robot is applying the pulley around the gear was incredibly challenging to get right and required more of that finely curated teleoperation data to get it to behave better. And additionally, we can do more sophisticated things like very quickly picking and placing this cassette tape and inserting it accurately every single time because we're able to collect data so well, because we understand the Markov process that we are defining by curating and building these behavior clone data sets. Another really important aspect of the project, though, was not just parallel mechanisms, but also grippers that could utilize tools. We can't, as researchers, deal with these more sophisticated problems if we're not providing robots with the dexterity required to do them. And so my team built these multiple degree of freedom grippers. We call them koala grippers because koalas have 2 thumbs. And what they were able to do is actuate each of the fingers individually and then actuate the full 2-DOF thumb, or I'm sorry, the 2-fingered thumb. And that would create different modes for grasping objects. And it was quite ergonomic as well. The operator was not very encumbered by utilizing this. And we're able to pick up a variety of different objects in the scene. We were optimizing for tools and power grasps in the environment, which was an important aspect of the problem. We wanted to also be able to singulate small objects, those fingernails coming in very handy in order to be able to do that. And also be able to singulate things like paper, which classically is very difficult for a Fenray style gripper. We could also handle more macroscopic tasks, such as picking and placing these much larger objects. And a human operator is willing to trust hammering a nail with this other gripper because they're able to receive that proprioceptive feedback, something that using teleoperation alone would be very challenging to do. And so this is one of the first autonomous policies that we were able to train. And that is made possible because it can singulate each of these cups because it is able to use those fingernails. That would have been very difficult to do with a different kind of gripper. So this is all in thanks to all of these amazing people who made all of this work possible. And I very much appreciate all of their contributions to this work. And now I want to talk about some of the more recent work I've been doing at Tutor with a lot of the fantastic people there, of putting together this 100 robot facility that we can collect a lot of high quality training data for. And so this is Data Factory 1, 100 robots in a room in Watertown, Massachusetts. At the time it was constructed, it was the largest data factory in the world. And what is happening here is there are a series of teleoperators located in all different kinds of regions of the world, collecting high quality demonstration data that we're able to use to train high quality policies. And so you can see some of these intelligent rollouts that we're doing, both from the teleoperators and from the autonomous behavior. And so I just want to show again the wave, because that is probably my favorite part. It's just so cool to see all of them being able to be commanded from a single computer at the same time. And so we actually have quite a capability to administrate all of the robots very quickly. This is the hardware setup. You can see that it is 2 6 degree of freedom grippers placed in a almost praying mantis style configuration with a camera in the head and a camera in the torso. And this is providing, and the 2 cameras in the wrists, this is providing 4 point clouds, which are then stitched together as a state of the scene alongside sort of the just RGB information and proprioceptive information that the robot's getting during data collection. And this is one of the autonomous policies that we were able to roll out with some of that data. So this is a clothing folding policy that is trained exclusively on this data. And this is a 1x speed video demonstrating that the robot is able to correctly perform all of the tasks that we've seen in lots of different policies but just using this distributed data collection system, which is very exciting. And this is some of the other autonomous behavior that we've been able to demonstrate so far with the robot itself that we're very excited about exploring further into the future. This is what the teleoperator sees as they collect data. You can see that they're getting a visual scene of the point cloud. They're getting the RGB streams, and they're getting the current live state of the robot. And this is us trying to reduce the embodiment gap as much as possible between what the robot is able to see and what the operator is able to see to reduce the privileged information that an operator typically has available to them. We've been trying to keep these robots online as much as possible. And so you can see that we're trending upwards to get full 100% coverage, which has been an exciting challenge to constantly maintain all of these different robots. 100 robots is a lot. And the other thing, of course, is you can't just collect data, you have to label it. And so we've been working very hard on getting curated labeled data to all of our researchers at Tutor and also the other engineers to make sure that we are collecting the best and most capable data we can. I want to thank all of the people that made this entire project possible. And there is no way it could have been done without all of their very important contributions. I do also want to mention, I work with Stephanie Telex on a blog called What to Tell the Robot, where we have defined the physically grounded Turing test. And we talk about sort of the future development of intelligent systems and how a lot of this is going to play out. I would encourage all of you to continue the discussion there. We're very responsive and always looking for more people to communicate with and build a community of very good researchers. And so the major takeaways that I want you all to think about are that we should be optimizing hardware and software together. I don't think that manipulation is just a software problem that all the hardware solved, and vice versa. I don't think the software is solved and it's just a hardware problem. I think that it involves having sort of uncomfortable conversations with your peers that are across the domain expertise aisle, that we should be thinking very carefully about how to collect our data, that online learning is going to be in our collective future, that we need to be finding ways to move beyond demonstration data alone, and how do we build a very good prior through all of this collection of high quality behavior cloning data. And then finally, to diversify your sources of data. I'm not a UMI purist, I'm not a teleoperation purist, I'm not a SIM purist. I want as much diverse types of data that represent the same kind of problem so that we can find the salient intermediate representations that are important for solving these problems. And then I'll just leave sort of this playing in the background. Happy to take any questions. Yeah. Yes, we only showed the point cloud to the operator alongside the RGB views, and yes, and the state of the robot that's live using a URDF. Yes. Not yet. We're collecting about as much data as we possibly can. Yes. So the uptime question is something I've been thinking about a lot. It's predominantly a hardware and engineering problem, that there's a lot of ongoing changes that people are making to make the data collection better, causes breaking changes, which requires better loops. And it's a lot of software engineering principles that can help mitigate those. But it is, unfortunately, when you're doing a full stack integration like this, very likely that you're breaking things. And something to keep in mind is that this is only a few month old project. There's lots of things that we're going to need to do in the near future to make this significantly better. And so I'm really excited about what the team has been able to put together in such a short amount of time. And you're sort of seeing a snapshot in time as we work to build an even better system. Yes.
Question about the operator. Have you noticed?
Yes.
Time like what is kind of learning and when you use humans to do any other stuff. When they are doing something, they do get more efficient outcome or in the same as with the teleoperation.
So the question was about, do I see the data collectors getting better? And yes, I do. I've been very impressed with how little information that the operator's been able to receive or how much delay there is, how good they are at sort of anticipating the entire trajectory itself. And so there's definitely a learning curve there. People who are better at VR tend to have a higher ceiling of performance. But there's still low-hanging fruit to get even more performance out of the data collectors that I think we're not quite 100% there on, but I've been very impressed with relative performance over time. And I saw this too, even with the Yumi work we were doing at Ray, that there was a huge difference in data collection performance between different data collectors. Yeah. So there are so many different modalities and so many underrepresented ones. I've looked at force a lot, and force is very important for some of these more dexterous tasks that we have because it disambiguates both the input and output to represent the state of the problem. It's more about, from visual alone, do I have enough information to be able to solve the problem? One of the cheats that we get as teleoperators is that I can overdrive the inputs. The robot can be in contact with the world, and because I'm training on the outputs of my controller, I am getting the forceful interaction data for free. But with Yumi, for example, you don't get that. If I'm applying force onto a scene using a Yumi gripper, the robot's not aware of that because it's not moving. What that starts to do is that starts to alias the output of your policy. So you're not able to actually be in distribution with what you saw during your training data because it's hidden to the model. And so there are parts of tasks like peg and hole where it's incredibly important to be able to apply that force. But things like audio can help disambiguate these things. Things like tactile can help disambiguate these things. It's about finding a stable representation of the problem. Okay, thank you very much.
And with this, we come to the last part of the workshop, which is aggregating some of this knowledge and then the voting for the most useful award.